Assalamu alaikum, I'm your teacher Rehan, and I'm back here with a new lecture of Physics class 10th. We'll be starting it from the chapter number 1, which is Simple Harmonic Motion and Waves. So before starting our chapter number 1 of Physics class 10th, we'll be having a short recap of class 9th. There were a few things you studied, basic few things you studied in class 9th. That was motion and the word vibratory motion. The word motion and the word vibratory motion. These two words you must have studied in your class 9. Now what was motion? Motion was that when any object changes its position with respect to the surrounding, this is known as motion. That object is said to be having motion. Now in simple words, if I explain it, it will be when an object moves from point A to point B, it covers distance and it is being observed by something else. Something else notices that it has changed its position. It was on A and now it's on B. So that object has motion. So this was motion. And another thing you studied in your class 9 was vibratory motion. So what was vibratory motion? The basic definition of vibratory motion was to and fro motion of any object by its mean position. To and fro motion of any object by its mean position is known as vibratory motion. In simple words, if I explain it to you, is that when an object moves to and back fro, and when it moves to and fro, it covers where it covers the distance, the mean position is between them. I mean that when it goes to and comes back to fro, so it passes from the mean position, then the object is said to be having vibratory motion. In simple examples, I will be giving you the example of the pendulum. Pendulum is the most simple example of vibratory motion, which goes from to back to fro and it passes from its mean position. Now here I have written something else beside of the vibratory motion. It's oscillatory motion. Both the vibratory and oscillatory motion are one thing. There is no difference between these two words. Words are changed, but meaning are the same. So our topic is simple harmonic motion, which we'll be studying in this lecture. What is simple harmonic motion? Simple harmonic motion is a special kind or a type of oscillatory or vibratory motion. A special type of oscillatory or vibratory motion is known as simple harmonic motion. This was the basic definition of simple harmonic motion, that's what it is. In simple harmonic motion, in our physics class 10 book, we have three things. The simple harmonic motion of mass attached to a spring, ball and bowl system, and simple pendulum. These are three things which we'll be studying in the simple harmonic motion of mass attached to spring. I'll be telling you that what is the phenomena of this concept and what is its basis. First of all, we have used displacement, restoring force, acceleration, mass and constant, denoted by displacement x, restoring force F, acceleration A, mass M, and constant by minus k. I'll be telling you that why it is minus k here. And first of all, I'll be telling you that what does motion of mass attached to spring says. It says that, I'll be explaining it through these three diagrams. Number one, it says that there are three positions of mass in this concept of mass attached to spring. Number one is extreme position B. Number two is means position O. And number three is extreme position A. Extreme position B, means position O, and extreme position A. In number one diagram, we can see that the object, the mass, is at O, means it's at the mean position. No any external force is acting on it. No any restoring force has been produced here. No, the spring is not compressed or nothing is happening. It's stationary here. So the mass is at mean position. In number 2 diagram, we will see that the spring has been compressed and external force has been applied on it. We have brought the mass nearer to the wall. So the spring has been compressed. The restoring force will be produced in the spring that it can bring the mass back to its original position, the mean position. And in number 3 diagram, you can see that we have pulled the spring outside. We have pulled the mass towards our body and the spring has been deformed. It will, restoring force is produced here, and it will have to come back to its original position with so. In number 1 diagram, the extreme position A and B were relaxed and the mass was at the mean position O. In number 2 diagram, the mass was at extreme position B, and in number 3 diagram, the mass was at extreme position A. So now I'll be telling you that what is the value of displacement, restoring force, acceleration, mass and constant right here in these 3 diagrams. In number 1 diagram, all the things will be 0 except mass, because mass cannot be changed, and constant. Now here is one very specific point in this mass attached to spring. Constant varies spring to spring. The constant K varies spring to spring. I'll be telling you that how this happens. For example, if you've seen the shocks of a car, they are very hard to compress them as compared to a simple spring. Another example is, yes, if I take the example of a ballpoint, the spring used in a ballpoint is very easy to compress. But if you look at the shocks of the car, they are very hard to compress. So each spring has its different constant value. The constant varies spring to spring. I'll be telling you that the displacement in number 1 diagram is 0, because the mass is at original position, means position. In number 2 diagram, what happens here, the displacement is covered in the negative side. It goes nearer to the extreme position B. It is not pulled up, it's pushed. So here the displacement will be produced. X will be produced. When I told you that compressibility is produced, so the spring will have to come to its original position back, its original form back. So for that purpose, when the restoring force has been produced in the spring, which will push the mass back to its original position. Acceleration. Now in class 9th, another recap of class 9th, it was said that force is equal to ma. Force is directly proportional to acceleration. If force increases, acceleration will also increase. So here we'll be saying that when force increases, the acceleration also increases with it. Force is directly proportional to x. The derivation, I'll be explaining it to you that how I've derived these values. The mass attached to spring says that when you apply a force on that mass, so the force which is produced, it will be directly proportional to the x. For example, how? If you look at this original position, nothing is happening. But here when you have applied an external force, so it has also covered displacement. If force increases, displacement increases. So here it will be that force is directly proportional to the displacement. Replacing the proportionality sign by is equal to in using the constant as k. Minus sign, I'll be explaining it to you further that why have we used here minus. K, now here what happened, x has been shifted toward that side, here it is multiplied, the next side it will be divided. So k is equal to minus f upon x, k will be shifted to that side, minus will remain here, so k is equal to minus f upon x. I have showed you that in Newton's second law of motion, we had used the formula F is equal to mp, we have derived it. So instead of force, we'll be using K is equal to minus ma upon x. I also told you that force is directly proportional to acceleration, right? When force is directly proportional to acceleration, here we said that force is directly proportional to the displacement, and here I said that force is also directly proportional to the acceleration. It's according to the Newton's second law of motion, and it's according to the motion of mass attached to the spring. Now, as I said that force is directly proportional to acceleration and force is also directly proportional to displacement, I said when force increases, displacement increases, force increases, so acceleration increases. So can I say that when acceleration increases, displacement increases, and when displacement increases, so acceleration will also increase? I'll say that acceleration is directly proportional to minus x, because the minus sign has been used here, I'll tell you that why are we using the minus sign here. So A acceleration is directly proportional to x. If displacement increase, acceleration will also increase, and if the acceleration increase, the displacement will also increase. So this was the derivation of this, and how the motion of mass attached to spring works. It has a very specific formula, no changes here with it. It says that T is equal to 2 pi square root mass upon K. It's a constant formula, it can't be changed. While we can find the value of mass and constant by shifting it toward that side and T by this side. Now actually I told you that why do we use, how does this motion of mass attached to spring work. And I'll be telling you that how does it function. It says that if you deform a spring, if you stretch a spring, and you release it back, so it will come back to its original position. I'll be giving you example. For example, if I have this mass attached to a spring, if I push and I stretch the spring, so here a restoring force will be produced, and when I release my external force, so it will go back fastly and collide back. So how does it work? When you stretch or compress, first I'll be telling you that when we compress a mass, a restoring force is produced in this spring, which will push back mass to the mean position. Now, at extreme position, I'll be telling you one thing. At extreme position B or A, the acceleration will be 0 or minimum. Acceleration or the acceleration at the extreme position A and B will be 0 or minimum. And what will be maximum here? The restoring force. Restoring force, as I told you, restoring force we represent by F, and the compress of spring and the stretch of spring, these produces the restoring force. The restoring force at the extreme positions will be at its maximum or at the highest peak. So when we compress it, the acceleration will be 0 because the mass is near it, and restoring force as the spring is being compressed, so a high amount of restoring force is present in the spring. It just needs that the external force should be taken out and it comes back to its original position O. When we remove our external force, so the spring will jump, the restoring force will act, and when the restoring force will act, so as I told you, acceleration is directly proportional to the displacement. Displacement was covered, acceleration will have to be produced as displacement has been covered. So as restoring force acts, we remove the external force and it is coming to its original position, acceleration will be produced here. It's a common thing when an object moves, it has acceleration. So when mass is coming to its original position O, it has acceleration that it's coming, otherwise it cannot come. A common phenomenon. When mass comes to its mean position O, so what happens here at its mean position O? The acceleration is maximum here at this position O. When it reaches at O, for example, if we have compressed it, release the force, it comes back to O. We pause a video here. We paused it here. The total setup has been paused and the mass is at O. So in class 9th again, you have studied inertia. When an object is in motion, so it tries to be in motion, and when an object is at rest, so it tries to remain at rest. When an object comes and it's having motion, according to inertia, it will try to be in motion. So what will happen? When a mass, it has acceleration, it comes to its original position, it is in motion, so it will try to remain in motion and it will not stop at point O. It will move further from its point O and it will come to the extreme position A. When it reaches its extreme position A, here, if you come here, the mass is at extreme position A. a high amount of stretch power is produced here. Restoring force just needs that it just needs to come to push the mass back to its original position. Here the mass will be again pushed to the original position O. The phenomena will happen, it will come to B, A, nearer, and a time will come that it will stop at point O. We cannot say that by just removing here in second part, if we remove the external force, so it will just directly come to point O, it will not go further. According to inertia and physics, it will go further, it will come to the extreme position A. And then it will go back because of the restoring force produced here. It will go back. Here again acceleration is 0 minimum. When it goes to point O, again acceleration is maximum. Again inertia. It will not go much nearer to it. But it will go nearer to it, but it will not touch the extreme position B. It is nearer, so it will again come to near to the A, B, and the time will come when it will come back to its original position O. So this was the actual phenomena of the motion of mass attached to spring. I told you that I'll tell you in the last that why do we use a minus sign here. It is that whenever you apply a force on that example, the external force which is applied on the spring, it decreases this displacement. Force applied decreases the displacement. The displacement is being produced. It's covered displacement, but it's going in the negative direction. That's why it's said to be in the minus k sign here and minus x sign here. This was our topic, motion of mass attached to spring.